Good morning everyone. Today our group will present our queuing model analysis on Kenangan Coffee Segamat for the subject QMT342. We observe the queuing system at Kenangan Coffee to understand how customer arrive, wait, receive service and leave the system. Our observation was conducted at Kenangan Coffee Segamat. The cafe operates from 8 AM until 10 PM. We observed the queue for 1 hour from 2:25 PM until 3:25 PM. During our observation, there were 2 servers working. Next is the arrival characteristic. First, the calling population is considered infinite because customer can continue arriving throughout the day. Second, customer arrivals are random and follow a Poisson distribution, meaning customers arrive independently at different times. Lastly, most customers are patient and are willing to wait until they receive their orders. Now let's move to the waiting line characteristic. The queue length is unlimited, which means customer can continue joining the line if more people arrive. The cafe is also uses the first in first out or FIFO rule. This means the first customer who joins the queue is the first customer to be served. Next are the service facility characteristic. Kenangan Coffee uses a single channel system where customers line up in one queue. The service process is a multi-phase system because customers first place and pay for their order before moving to the pickup counter. There is also only one waiting line for the customer. This diagram shows the complete customers flow. Customers first arrive at the cafe. They waited in line before placing and paying for their order. Next, they move to the pickup counter to collect their drinks. Finally, they leave the cafe after receiving their order. The service time follows an exponential distribution, which means the service duration varies from one customer to another. Finally, this table shows the observation data we collected during our 1-hour study. We recorded each customer's arrival time, queue time, order start and end time, and service start and end time. These data were later entered into the QM software to calculate the queuing performance measures, which will be explained in the next section of our presentation.
Next, this slide shows that QM4 Windows output for the first phase, which is the order counter. The arrival rate is 11 customers per hour, while the service rate is 18 customers per hour, with 1 server available. The average server utilization is 0.61, which means the server is busy 61% of the time and still has enough capacity to serve customer efficiently. The average number of customers waiting in the queue or LQ is 0.96, which means there is approximately 1 customer waiting at any given time. The average number of customers in the system or L is 1.57, meaning around 1 to 2 customers are either waiting or being served. The average waiting time in the queue, WQ, is 0.09 hour or about 5.24 minutes. The average time spent in the system, W, is 0.14 hours or about 8.57 minutes, including both waiting and service time. Overall, these results show that the order counter is operating efficiently because customers experience on. Next, this table shows the probability of having different number of customers in the order counter system. We can observe that the highest probability occurs when there are only a few customers in the system. As the number of the customers increases, the probability gradually decreases. This means that most of the time the queue is short and it is uncommon for many customers to be waiting at the same time. Therefore, the probability analysis supports our previous finding that the order counter is operating efficiently and low congestion. This slide presents the sensitivity analysis for the order counter. The analysis shows how the system performance change when the customer arrival rate increase. As the arrival rate become higher, the server utilization increase. The queue length become longer and the waiting time also increase. This means that during busy period, customer will need to wait longer before placing the order. Therefore, if the customer demand continues to increase, Kenangan Coffee should consider improving service efficiency or adding another server during peak hour. Next, this slide shows the QM output for the second phase, which is the service or pickup content. The arrival rate is 11 customer per hour, while the service rate is 13 customer per hour with one server available. The average server utilization is 0.85, which means the server is busy 85% of the time. This is much higher than the order counter, indicating a heavier workload. The average number of customers waiting in the queue, LQ, is 4.65, meaning around 5 customers are waiting on average. The average number of customers in the system, L, is 5.5, meaning about 5 to 6 customers are either waiting or being served. The average waiting time in the queue, WQ, is 0.42 hours or approximately 25.38 minutes. The average time spent in the system W is 0.5 hours or 30 minutes. These results show that the service counter experiences much longer waiting time than the order counter, making it the bottleneck of the system. Next, this table shows the probability of having number of customers waiting at the service counter. Compared with the first phase, the probability of customer waiting is much higher because drink preparation takes longer than taking order. As the number of the customer increase, the probability decrease, but the service counter is still more likely to experience congestion than the other counter. Therefore, this probability table confirms that the service counter is the busiest part. This slide presents the sensitivity analysis for the service counter. The analysis shows how changing the number of servers affect the queue performance. We can see that when more servers are added, the server utilization decreases, the queue length becomes shorter, and the customer waiting time is reduced. This means that adding another staff member during peak hour would improve the service process and reduce congestion at the pickup counter. Therefore, we recommend adding one more server during busy period to improve customer satisfaction and reduce waiting time.
Now, I will explain the calculation for the first phase, which is the order counter. In queuing theory, we first calculate the utilization factor represented by the simple P, which is rho. The utilization factor measures how busy the server is. It is calculated by dividing the arrival rate lambda by the service rate mu. If the utilization factor is close to 1, it means the server is busy almost all the time, and customers are more likely to experience long waiting time. If the value is much lower than 1, it means the server still has enough capacity to serve customers efficiently. For our observation, the utilization factor is below 1, which indicates that the order counter is able to handle customer arrival efficiently without becoming overloaded. Next is penal, or the probability that the system is empty. This means the probability that there are no customer in the system, meaning no one is waiting and no one is being served. A lower value of penal means customer arrive frequently and the server is busy most of the time, while a higher value means the server spend more time idle. Overall, these two measurements show that the order counter operates efficiently and can serve customers without excessive congestion. The next calculation is LQ, which represents the average number of customers waiting in the queue. For example, if LQ equal to 2, it means that on average, two customers are waiting before being served. A smaller value of LQ indicate that customers do not have to wait for long. Next is L, which represents the average number of customers in the entire system. This includes customers who are waiting in line and customers currently being served. Since our values are relatively low, it shows that customer traffic at the order counter is well managed and the queue does not become too long. Therefore, the order counter provides efficient service during the observation period. This slide focuses on the waiting time. The first measurement is WQ, which is the average waiting time in the queue before customer receives service. From our calculation, we equal 0.09 hour or approximately 5.24 minutes. This means customer only wait around 5 minutes before placing their order. Next is W, which is the average total time spent in the system. This includes both waiting time and service time. The value is 0.14 hour or approximately 8.57 minutes. This tells us that from the moment customers join the queue until they finish ordering, they spend less than 9 minutes. This is considered an efficient service time for a busy coffee because customers are served relatively quickly. Now, we move to the second phase, which is the service counter. Unlike the order counter, this phase includes preparing drinks before customers collect them. First, we calculate the probability that the system is busy. This tells us how often the service counter is occupied preparing drinks. A higher probability means staff spend most of the time serving customers. Next, we calculate the probability that the system is free. This shows the chance that no customer is waiting for drink preparation. Since preparing coffee takes more time than taking order, the service counter is naturally busier than the order counter. Therefore, congestion is more likely to happen during this stage. Now, we move to the second phase, which is the service counter. Unlike the order counter, this phase includes preparing drinks before customers collect them. First, we calculate the probability that the system is busy. This tells us how often the service counter is occupied preparing drinks. A higher probability means staff spend most of the time serving customers. Next, we calculate the probability that the system is free. This shows the chance that no customer is waiting for drink preparation. Since preparing coffee takes more time than taking order, the service counter is naturally busier than the order counter. Therefore, congestion is more likely to happen during this stage. Finally, we calculate the average waiting time. WQ represents the average time customers spend waiting before the drink are prepared. W represents the total time spent in the service system, including both waiting and drink preparation. These values help us evaluate service efficiency. The results show that customers spend more time at the service counter than at the order counter. This does not necessarily indicate poor performance, but rather reflects the additional time required to prepare each beverage. Overall, the service counter performed reasonably well, although improvement could prove reduce waiting time. In conclusion, our study was conducted at Kenangan Coffee Segamat from 2:25 p.m. until 3:25 p.m. Based on our observation and calculation, customer arrival follow a Poisson distribution, while serving time follow an exponential distribution, making the queue suitable for analysis using the MM1 queuing model. Our findings show that order count performed efficiently with a short queue and an average waiting time of approximately 5.24 minutes. However, the service counter experienced higher congestion because during preparation requires more time than taking customer order. Even though waiting time is slightly longer at the service counter, the cafe still provide good overall service and customers are served within a reasonable time. To improve customer satisfaction further, we recommend adding one additional server during peak hour and improving staff scheduling to reduce congestion at the service counter. Overall, Kenangan Coffee demonstrate an efficient queuing system with only minor improvement needed during busy period. That's all from us. Thank you.